I'm going to show you the product rule. I'm going to prove it for you. Okay. You don't have to reproduce the proof, but I want you to know where it comes from. Okay. So let's start off with a definition. Okay, so here's where I'm going to start. I've got my function y, but it's a product of two other functions, okay? Like x squared and x squared minus 1, just like we were dealing with, okay? So if I've got a product here, what would be its derivative? Well, so far when we want to work stuff out, we always go back to first principles, and that's exactly what we're going to do here, okay? So think about this. Usually we'd say, you know, if y is a function, we want y dash. How do we define first principles? What do we start with? Thank you. We start with the limit. As h approaches 0 of... Now just quote it for me. Just normal, basic first principles. What's on the top? F of x plus h minus... Okay, so that's the rise. And then you've got the run. Happy so far? Okay, good. Now in this case, our f is a little more complex, right, or complicated. It's got these two bits to it. So what I'm going to do is I'm going to take this, and instead of f's, I want u's and v's. Okay? What's it going to look like? Well, this next line is going to be... Before I do it, I want you to have a go. Write it down. What would you put as your next line? If I want to get rid of all the f's, replace them with u's and v's, because that's what I actually have. What would your next line look like? I'll give you a second to think about it and jot it down. Okay, does it match? It looks like an awful mess, doesn't it? But all I've done is I've just replaced f's with u's and v's. You can see there's the product. Okay, I'll put some color around it. There's the first product, and there's the second one. Okay, you can see f of x, u v. Okay, so it's just a straight substitution. Now at this point, what am I going to do? In order to get to the product rule, things are going to look a lot worse before they get better. And so, before I do this next step, I just want to remind you, in maths, we learn techniques like this, like say, rationalizing the denominator, right? So if I gave you this, okay, in order to make this simpler, we first make it more complicated, right? We multiply by extra stuff so that we can, you know, expand this with difference of squares, and eventually it looks better, right? In the same way, you know, when you're doing a circle, okay, and I give you something like this. I don't know. If I gave you a circle and I say, tell me the center and the radius, okay, what do you have to do to this to work out the center and the radius, those features? You've got to complete the square, right? Which is adding stuff, and then it gets bigger, and stuff is getting worse, just like with rationalizing, before it gets better, okay? So I'm going to make this look a lot worse in order to get to something simpler, okay? And by the way, if you're trying to do columns down your page, they're about to explode. This is going to get very quiet, okay? So here's what I'm going to do. On the numerator, I'm going to add something and I'm going to subtract something so that my net difference is 0. Sort of like here, you multiply and you divide by something, okay? Now what I'm going to add and subtract will look a little counterintuitive at first, but hopefully the reason why will come out in a minute. Okay, so we start with a limit. And I've already got this out the front. Okay, now what I want to add here is, let me think to myself. I think I want this. Hold on. No, I want this. Minus x plus h v of x. Is that right? Yes, good. I've subtracted this weirdo looking term, okay, which is kind of like a cross between these two. Since I've subtracted it, in order to actually not muck around with my fraction, I'm going to add it as well. Okay? So I'm going to get this. I told you your columns are going to break, right? Minus this. Okay?
Gross.
Bam. Okay? Alright, so just to make sure you know what you're doing here. And you might like to, because, you know, when we're doing this and we're working it out as we go, everything makes sense right now, but in like a week or a month, you're going to come back and you're like, what's going on here? Okay? So maybe in another color, put in for yourself. Okay? Extra term, added and subtracted. Sorry. Added and subtracted. Okay? You may even like to put for yourself a reminder that this is very, very similar to what we do with rationalizing denominators. You multiply and you divide by the same thing, so there's no real change. Okay. Alright, now, what have I got here? You can see this particular term that I've added, subtracted, I can factorize, I can pair up of these 4 terms. I can pair them up in different ways. Okay? So I'm going to write that down like so. My limit's at the front. And here, the first 2, the common term is, what can I factorize out? Good. U of x plus h. Okay? And then what I'm left with is v minus... Okay, there's the first one. Over here, the common factor is just v, right? V of x. Okay, so there's it out the front. And what I've got in the brackets is u of x plus h minus u of x. Okay? All over h. Okay, happy so far? Alright, now, why have I done this? By the way, the reason why I added and subtracted this is just so I can get to this factorization. What's useful about this factorization? Much like what's useful about, you know, the conjugate, that factorization is helpful. Here, in this case, it was difference of squares. What do I have here? Let me try and make it a little more obvious to you. Okay, I've got 2 terms here on the numerator. So really, I can break this apart into 2 fractions that are completely separate. Okay, there's this one, which is over h, right? And I've got this one, which is over h. Is that okay? All right, now, just for a second, ignore this right-hand side fraction. Just look at the left-hand one. Okay. Are there any features in there that look familiar or useful? Yeah, do you see something?
You know, when it says v of x plus h minus v of x,
Yep.
isn't that just v of h?
No. Just like this is not just f of h. But it is something important. We're onto something. What's going on? What's the important feature? We're on the right track though.
Like first principles.
Oh, how suspicious, right? Look at this guy, right? Over h, and we're taking the limit. Does this not look identical to what we had in the first line, except with v's instead of f's? Okay, and you also have this weird pesky guy out the front. Okay, so in order to make this a little better, I've got really 4 things here. Okay, 1, 2, 3, and 4. So what I'm going to do, I said it was going to get worse, right? Is I'm going to take all 4 things and take the limit separately of all of them. Okay? I'm going to take the limit of every single one. So, watch this. Here we go. At the front, I've got limit as h approaches 0 of the first term, which is just u of x plus h. Is that okay? Then I multiply by the limit of this whole fraction that's left. So I've got limit as h approaches 0 of this guy over h. I've left these 2 as the fraction together because, like I said, it looks just like first principles. Okay? So there's my first 2 limits, and then I have another 2 over here as, h approaches 0 of v, and then limit as h approaches 0 again. Now, can you see why I told you to ignore this side? Because basically, it's just like the first, but with u's instead of v's. Okay? So again, just like we did here, you might like to put down some extra description for yourself here. Why are we doing this? Why are we breaking it apart into so many pieces? To make first principles obvious. Okay? It's there twice. Okay? Alright, so I told you that I broke your columns, right? But fortunately for me, I have bigger columns than you, so I'm going to keep on going over here. We've got 4 limits, okay? Let's just consider them one by one. Number 1, u of x plus h. As h approaches 0, the whole point of doing first principles and that kind of thing is to simplify as far as you can so you can just put that limit in, so you can evaluate the limit. And I've got no problems here. H is not on the denominator, so I can just slap in h equals 0. So when h equals 0, that limit is just u of x, isn't it? The h is gone. Okay. Now we said this guy was like first principles. This is what you get when you're trying to differentiate a function. Okay. So this is v dash x. Is that okay? Alright, then you get the next part. This is even easier than the first one. What's v of x as h approaches 0? Well, it has nothing to do with h, right? So it just keeps on rolling on and doesn't care what value h takes. So it's just v, okay? And then your next part is u. Okay? So, I can just write this without my all of my brackets, because they're just really giving me a bit of extra information, telling me that all of these letters, right, they're not just pronumerals, they're actually standing for functions of x. But to make it neater, I'm just going to write it without them. I'm going to write it like this. I'm going to reverse the order, actually. And there's the product rule. Maybe, if I put it out the front, what was I actually differentiating, right? What did I start with? I was differentiating u times v, right? So the derivative of u times v, if u and v are functions, not pronumerals, okay? Here's the way I remembered it when I got taught it. You start with an uv and you end with a vuv, okay? Yeah, okay. It's not a corny acronym, but I don't know. Like,
that's the weirdest way to
yeah. You could be like start with an ab and then end with an aber or something, but I don't know if that's an improvement or if it's worse. Anyway, now by the way, you might be wondering, I had u's first here, and why did I put v's first here? The reason why is when we get to the quotient rule, even though here the order doesn't matter, it's a sum, so you can take the order whichever way you want. With the quotient rule, which we're going to look at later, the order does matter, and this is the order it must be in. Okay, so you'll see that later, but I figure you've got enough rules to remember. I want to try and make them sort of closer to each other so you don't have to remember as much. Alright? So, that's the product rule. Can we come back to our example? We said the derivative of x squared times x squared, was it minus 1? Minus 1, I think. Yeah. Okay, so how do you do this? Like I said, I know you can do this by expansion, okay, but later on we'll meet the kinds of functions that you can't just expand out. So let's practice what we're doing here. What I do when I see a product is I get out another color, or if you're lazy, use the same color, and I label each function. Okay? Now again, because it's a product, the order doesn't matter, right? This could be v and this could be u, but I just put them in alphabetical order. Okay? So the derivative of an uv is a vuv. Okay? So here we go. I write this down, again, it's a formula, not because it gets marks, but because it just helps me remember what's the right steps I've got to go through. So, what's v? It's x squared minus 1. Okay? So I just slap the whole thing in there. Okay? And then I'm up to u dash, which is the derivative of this first part, which is 2x. Okay, good. Then we take it in the reverse order. So now I put in u, which is just x squared. Okay? And my v dash, which we already established, was 2x. Okay? So now when I expand this all out, you get your 2x cubed minus 2x plus 2x cubed, which is 4x cubed minus 2x, which is what we got in the first place. Okay? So product rule, it works. Okay. Does anyone have any questions about any of these steps? Like I said, you don't have to reproduce this thing. But I still want you to understand, like, where does this come from? Like, if I had just given this to you at the beginning, you'd be like, oof, oof, what, why? I don't know, it just works, okay? This is why it works. It's a legit result, and it just makes sense because of first principles, which you already understand. Okay.